Good afternoon, everyone. Welcome to the second session in the afternoon. My name is Thomas Baskol from the ITU, International Telecommunications Union. In this session, we are going to talk about tinyML for good, how tinyML can be used to achieve some of the sustainable development goals. So we have two speakers in this session. We have Massimo PAVAN from Politecnico di Milano and Jonah Besens from CSEM. So the first talk will be by Massimo. He's going to talk about smart and tiny UWB radar sensors, a distributed solution for enhanced home care. So the floor is yours, Massimo.
Sorry, I don't have a manner of making the presentation go ahead. So, hi everybody. In the meantime, I'm Massimo. I'm here to present my work on smart and tiny ultra-wideband radar sensor. The work was done in collaboration with my advisor, Professor Manuel Roveri, with Pierpaolo Lento of TrueSense SRL, and Alessandra Fiore, a thesis student of ours. Okay, can I? No? Okay. Okay, let's start from the first slide. I wanted to start my presentation with this. Okay. So spoilers of the presentation here. Let's start maybe from this. The motivation for the adoption of automated elderly care solution, which is what I wanted to talk to you about today, I think that can be really summarized from the plots. Okay. Have you found it? Huh? Oh, okay. Sorry. Thank you. Okay. I'll try to restart from here. What I wanted to start from is the article from The Guardian. It's actually a few years back that describes more or less the problem that we are trying to target. And is saying that the future of elderly care, it will involve for sure artificial intelligence. Starting from the example of a girl whose father was, she found him one day opening 6-7 boxes of cereal in the early morning and pouring milk directly on them. That was an early sign of elder dementia, and she later on adopted an elderly monitoring solution. And what I want you to focus is the last part, the highlighted part, which says that she's now feel a lot more safe, because now she would have got an alarm as soon as her father would went to the kitchen and that morning, because it will be something that really would have been really out of the ordinary with respect to the habits of their father, of their parents. So the motivation for the adoption of automated elderly care solution, I think, can be summarized by these slides, which I'm pretty sure you're have already seen somewhere else. On the left, we have the population pyramid of Italy in 1950 and the population of Italy more or less today. As you may grasp from this graph, is that the population is aging quite rapidly, and at the same time, the working population, the working age population is shrinking down, causing also a shortage of caregivers that can take care for them. Furthermore, the articles also highlighted that the fact that nowadays families do want their relatives to stay in their home as much long as they can. Current solution for elderly monitoring encompass constant human presence, but as we have seen, that is becoming more and more costly every day. Possibly smart surveillance camera, possibly smart, again, wearable devices, maybe based on waistbands, or, for example, solution that control the motions in rooms, like peer sensors. There are, of course, some risk correlated to these technologies that goes beyond the mere technological risk that could include the working condition of the device. For example, camera-based device could not work in dark condition or with obstructed vision. But for example, if we are working with machine learning, also biases in the dataset. But we have also other types of risk, which involve, for example, ethical risks and social risks. From the ethical point of view, for example, a lack of the privacy of the privacy preservation for the final user, or the fact that the solution that we are proposing are invasive in the sense that they need to be constantly cared by the patient, or also the direct rejection of the technology from the patient that we want to monitor. While social risk mainly goes in the direction of social isolation of the patients, in the sense that if we just rely on this technological solution for the monitorance of elderly people, they could feel isolated from from human contact. And of course, there is also the possibility that the patients, as highlighted by the article, as I was mentioning, modify directly their habits in order to not trigger the solution that we use, in order to make not worry their relatives, for example. And so we need to really be careful when we design this kind of solution. We really need to check that our solutions are, first of all, technically sound, that they consider the specific requirements of the environment that we are working with, and are able to adapt also to each individual's patient's lifestyles, trying to lighten the burden on the caregivers, but also without trying to substitute them. So for today, I'm presenting a solution in this context that works with ultra-wideband radar, which is a new technology that has some really interesting advantages compared to the previous one that we have seen before, that relies mainly in the fact that they are really privacy preserving, since from the data, as you may see them in the picture above, it's very difficult to identify the identity of a person. They are non-invasive, since they do not require to be constantly carried by the patient, and they can provide high precision data in the order of the centimeter with a fast execution and a low energy consumption. In this context, ultra-wideband radar and tinyML can really be interesting to put together, because ultra-wideband radar are currently becoming cheap, tiny, and also omnipresent, since we can find them also on high-end recent phones. They can be sold for a few dollars. They are usually MCU-based and often battery-powered. At the same time, they provide a quite noisy signal, as you may see in the picture, high-dimensional in the sense that it's a matrix of time and space, and it's almost impossible to interpret the signal with just signal processing techniques. Some example of the usage of ultra-wideband can be seen in some of our previous work, which dealt with the task of presence detection of human, subject recognition, which basically means to understand if the subject is a child, an adult, or an older person, and people counting in environments like the back seats of a car or home environments. The solution that we have proposed in this work are tinyCNN, a family of tiny convolutional neural network model for this task, with their variation tinyCNN-C for multi-class classification and tinyCNN-R for regression instead. All of this work in streaming on an MCU-based device. The lesson that we learned so far by working with this type of radar is that it can be difficult to work with this data for machine learning, mainly because very few datasets are currently available for this type of sensor, and that even small differences in the sensor can make huge differences in the data that we obtain from them. Also, different methods of reprocessing may lead to very different data in the end. Overall, there is quite a lack of standardization that, in my opinion, can go beyond the ultra-wideband context, but can be seen also in many other non-conventional sensors, like, and with non-conventional I mean something different from cameras, microphones, or IMUs. So the solution that I'm presenting today is a proof of concept for the elderly monitoring with a solution that relies on multiple sensors, placed one each in each room of the house that we want to monitor, that runs, in which each sensor runs a tinyML algorithm, which outputs presence and distance of the target that we are monitoring. The outputs of this sensor are then collected by an edge device, which is running an anomaly, and with anomaly I mean something like we have seen at the beginning of the presentation, an anomaly detection algorithm, trained and personalized directly on the data of the patient. The sensor that we use is this one from NXP, and the constraints that we set for this problem are the one that you can see here. So roughly 200 kilobytes available for ML on device, an execution time that should be below 1 second, and this time, no particular requirements on energy consumption. But other times, as for example in car, we have also energy consumption requirements. So the presence detection problem is pretty simple. We just need to see if a target is present in the room or not. And we utilized a version of the previously mentioned tinyCNN that run continuously on the device. While for distance estimation, what we want to output from the sensor is an estimation of the distance of the person from the radar itself in centimeters. The architecture that we are using are this one. They are pretty simple, and the main differences are in the end part, which use a fully connected layer in both the architecture, but with a sigmoid activation function for the problem of presence detection, which is binary, and a linear activation function for the problem of distance estimation, which is instead a continuous problem. The results that we obtain on these two tasks are roughly of 0.9% of accuracy on the test set for presence detection, with an algorithm which is requiring less than 30 kilobytes of RAM memory and is able to execute in the device in under 0.2 seconds. While for distance estimation, we obtain a mean absolute error of 15 centimeters, with a memory requirements of roughly 90 kilobytes of RAM memory. The complete pipeline in which this algorithm should be used involve also the usage, as I was saying, of an edge device, which is collecting the output of this tinyML algorithm in all the rooms, windowed with a window of more or less 1 minute. The time series of cumulated results are then analyzed by the anomaly detection algorithm that we will see in a moment. Starting from the data, the multivariate time series that we are dealing with is something like this, in which we have the time, of course, and for each room, the presence of the person, and if the person is there, also the average and standard deviation of the distance of the patient from the radar. The average distance gives us an idea of the position of the patient, while the standard deviation gives us an idea of the level of activity of the patient. So if he is active or if he is instead standing still. The adaptive anomaly detection algorithm is meant to acquire some data in the first period of usage of the device. And with data, I mean the outputs of the ultra-wideband sensor present in the house. If no anomaly is signaled by the carrier, those data are considered nominal, so we do not need even a label collection for that kind of data, because the anomaly detection algorithm that we will be using is a one-class classification algorithm. The algorithm can later on, during usage, can be retrained if false positive or if an anomaly that it was not present is detected by the carrier. With this one-class classification algorithm, we can potentially detect any type of anomaly, which means something different with respect to the habits of the patient that we have collected in the first phase of the device. The algorithm that we use for this part of anomaly detection is a one-class SVM based on a kernel with radial basis function. And the anomalies that we have tested this algorithm on are like two presence in the house when only the patient should be there, the absence of the patient during the night, the presence in other rooms also at night, or, for example, presence of a subject when he is usually out. So what I would like you to take home from this presentation is that also data generated from tinyML-enabled sensor can be used successfully as input for other machine learning algorithms later on in a pipeline, enabling also the adaptive unsupervised algorithm to be coupled on them in order to obtain a solution which is highly personalized on the habits of the patients and their carers. Future works will try also to reduce the requirements of the on-device learning algorithm on the edge device to make it fit in a tiny device. If you're interested in these aspects, you can come later on to my poster. And of course, also to improve the reliability of the tinyML algorithm, mainly by improving the data that we are working with. I thank you a lot for your attention, and if you have any question, I'll be more than happy to respond.